All right, so it's the best time of day once again. So at least for me, it's the best time of day. So I haven't posted homework yet because we don't really have enough at this point to send you guys out after today. So like this evening, I'm going to post a homework assignment for the week, and then because of the way that the lecture is set up this time. If I need to push the quiz back till next week, I will. I'm not sure yet. I think I'll have enough. There'll definitely be enough done so that we'll be able to have a productive lab day this week. I may slide everything back by a day. We'll see. But tonight the homework will be posted, and it will be the beginning of integration. Will be what that covers. So what we're talking about, and what we started talking about last time, was complex integration. And so I think last time we had the following ideas that we had set up before we stopped, right? So we talked about simple closed curves, where simple meant that it wasn't self-intersecting, and closed meant it loops back on itself. We talked about smooth curves, whereby smooth, so this smooth means C1, right? So differentiable curve. That's another way of thinking about that. Simple meant non-self-intersecting. This board is so bad. This building is so new. Closed means a loop. So it's a loop, non-self-intersecting, C1. One thing I did not say last time that we're going to want to have available is piecewise smooth curve. So if I call a curve piecewise smooth, what I mean really is that C is equal to a union of curves. So say, I don't know, J is equal to 1 to capital N of Cj, where each Cj is smooth. And then I guess without devolving into the notation for this, the idea is the end of Cj is the beginning of Cj plus 1, right? That they intersect at one point. So you've got something like this. If this is C1, then there's a join point, and then we have C2. And the joins don't have to be smooth, but the pieces have to be smooth, right? So C1, C2, C3, this would be a piecewise smooth. Let's actually make it a loop here. So this piece is C4, and then back up here for C5. This would be a piecewise smooth, simple, closed curve. Okay. So last time we set up the notion of integration. It said that the integral over C of f of z dz was equal to the integral from a to b of f of z of t. And then, actually, I think the notation that we set up here was that this was f of x plus iy times x prime plus iy prime dt, where z of t is equal to x of t plus iy of t. Right, so that's sort of our basic definition of contour integration was this. I mean, it's line integration from calculus 4, right? You have a path. You plug the path in, and you just use regular old real calculus to do the question. And before I go into, there's some really important examples I want to talk about. And before I do that, I at least want to talk about how this definition links up with the idea of piecewise smooth curves. And it's in the obvious way, right? If you're going to integrate around a curve that's piecewise, you just integrate it on each piece and then add the integrals together. So if C is piecewise smooth, say C is equal to a union of Cj, then the integral over C of f of z dz is just equal to it's the sum over the pieces of each of the integrals individually. So f of Cj. So you just break the integral up. You already did this in calculus 2 when you learned integration, right? This is essentially the same as the rule that says that if you have a to c of f dx plus the integral from c to b of f dx, that this is really secretly the integral from a to b of f dx. It's the same rule. If you're integrating over pieces, you just glue the pieces together. Okay, so that's kind of what we did last time. We set up a notion of integration. we set it up this way because complex functions are 2 real dimensions in and 2 real dimensions out, and this is a way of getting a handle on what's going on when we integrate things. I want to show you the sort of an observation that underlies all of complex analysis, like what happens next in complex analysis, which is the exercises that I offered on Thursday last week, the lab day, that like 3 or 4 people actually did, but they're important enough that we should all see them, okay? And so the idea here is we're going to integrate this. We're going to integrate z to the n dz over a circle where c is just the contour given by r e to the it, where t travels between pi and minus pi. So essentially, we're integrating the function z to the n. We're integrating around a circle centered at 0. So this is z is equal to 0. And then we're imagining that we've got some circle of radius r. And we're traveling from this point at minus pi, which is the negative part of the principal argument, and we're coming all the way around to pi. And so let's actually just do this. Okay, there's one additional assumption I need to add here, which is let's make sure that n is not equal to -1, and we'll treat that case separately. It'll be clear why we need to separate that case out once we actually do this computation. So we're going to do this integral. And so we're okay to do the integral, of course, because as far as I'm aware, circles are smooth, differentiable curves, right? I mean, this is a nicely differentiable function. If you like, you can think about this as r cosine of t plus I times the sine of t. Cosine and sine are differentiable, so it's I guess I forgot an r here. Not an ellipse. There, that's better. Same thing, right? Pieces are differentiable, it's a smooth curve. So let's just plug in. I mean, if z of t is equal to re to the it, then the integral of z to the n dz around that circle is the integral from minus pi to pi of, okay, e to the it to the n times d, oh man, okay, so dz is the t derivative here. So we get ire to the it dt, just by the chain rule. Feel free to double check me here and make sure I don't make any algebra errors. What's that?
Are you missing an r inside to the n?
I am. R e to the I t to the n, and then dz is I r e to the I t dt. So I'm going to collect everything together. This is a dt integral. The integral from minus pi to pi of, let's see, so there's an r to the n, and then an e to the int, and an I, and an r, and another e to the it. So collecting everything together, I get r to the n plus 1, e to the I n plus 1 t, an I that I'll pull out here, and there's a dt. And this is actually right here. This is why I excluded the case where n was equal to -1. Because if n is equal to -1, this isn't here. Right? This is ei to the 0 in that case. So everything is going to cancel. So when -1 is here, none of this stuff is here, and we're going to treat it separately. Okay? So this is why we've excluded the case where n is equal to -1. Now, this is just a t integral. We're going to use the fact here that even for complex numbers, the integral of e to the ct dt is equal to 1 over c e to the ct plus some constant k. That still works. Integration of any e to the constant times t is just 1 over the constant times e to the ct. So if you actually go through and integrate this, this is way less intimidating than it looks, because all you're integrating is e to the ct. So what you get here is, okay, so we get I r to the n plus 1. We'd better divide by n plus 1, and then I have an e to the I n plus 1 t evaluated from minus pi to pi. So the observation here Have I made a mistake?
No.
Have I not made a mistake?
The I cancels.
So the observation here is that this is 2 pi apart. Yep.
Did you forget to pull the I into the denominator when you took the integral, and so the I's cancel?
Oh yeah, there's an I. Yeah, sorry. Yeah, yeah. The I is actually part. This whole thing is the constant, right? Yeah. So I should have pulled an I down here. Right. It doesn't matter because what's going to happen is we're going to get 0 out of this thing anyway. Because what happens? Well, what's e to a constant multiple of I pi? I mean, this right here is, if you actually evaluate it, you get some constant that you don't care about, n plus 1, n plus 1, e to the I n plus 1 pi minus e to the I n plus 1 pi, but with a negative sign in front of it. But those are the same number because they correspond to the same point on the unit circle, right? This is the point on the unit circle that sits at pi. And this is the point on the unit circle that sits at minus pi. And those angles are the same, which means you're at the same point on the unit circle. If you actually compute this, I think what you'll find is that they're both equal to minus 1. So you have minus 1 minus negative 1, which is 0. And that's weird. If n is not equal to, notice, the only restriction we had to make on n, assuming n is an integer, the only restriction we had to make on n here, in fact, even if n is an integer, but yeah, let's leave n an integer so we get a 2 pi gap. If n is an integer, and we integrate around this circle, we get 0 out of z to the n. Well, that's weird because, I mean, I think what that immediately implies, if you think about it, is suppose you did the same integral. Here, let's be extra pedantic. Yep.
I understand how e to the I pi is equal to e to the I negative pi,
Uh-huh.
but we have those n plus 1s in there, and doesn't that change the value of where we are on the circle?
It tells you how to wrap, right? But the point is that like an integer multiple of this thing is not going to change its value because if you change the 1 to, I mean, what's going to happen here is you can imagine, pick different values of n, like pick n equals 0, right? You get pi and negative pi. Pick 2, and you get minus 2 pi and positive 2 pi. Pick 3, right? The thing is, no matter where you are, you're landing at the same point, no matter how you go, because
So are we only dealing with z to the integer power?
we are, because this is ultimately this is motivated by power series, and so for our purposes right now, we are examining the case where these are terms of power series. So don't think about rational things yet, right? This is just integers. N is some integer. I should have made that assumption at the beginning. Here, I'm making the assumption that n is an integer, but not equal to negative 1. Okay? Okay, so that means you can start proving all kinds of weird stuff, like, hey, if I set this whole situation up but I put a polynomial inside the integral, what is equal? 0, right? Polynomials are made out of z to the n's. So if you did an integral around that same circle of any polynomial p of z, if you wanted to be extra pedantic about that, you could write it as the integral over c. What is a polynomial? Well, it's a finite sum of some constant ck times z to the k, where k runs from 0 to capital N of dz. Finite sum, right? This is just a way of writing a polynomial in z, right? But for finite sums, there's no problem with switching integrals and sums. We do that all the time. We integrate term by term. So we could write that as the sum from k is equal to 0 to n of the integral over c. Well, ck is a constant. That comes outside of the integral. That's just a pile of zeros. Huh. That's weird. Yep.
How did you justify taking the limit out of the integral?
The limit?
Oh, sorry.
It's finite. It's finite.
Okay.
It's only because it's finite, right? So sums, if you have a finite sum, right, the integral of a plus b is the integral of a plus the integral of b.
Right.
Just by definition, you can do that.
Okay.
It's only because it's finite. This is much harder to justify if that's an infinite sum.
Right.
Okay. This is basically saying the integral of f plus g is equal to the integral of f plus the integral of g. And if you want to do it for 3 terms, you just do 2 and 1 and then split the 2, right? So for a finite sum, there's nothing to prove here, just from the definition of integration. Partly the reason I'm laying it out like this is because I'm trying to get used to this notation, right? That this presentation of integration is the way that this looks now in this class, right? In words, what we would say is that the integral of a polynomial around a simple closed curve. Now this is a bigger statement than what I just showed right here, but it turns out that you can extend this to any simple closed curve. Not just the circle centered at 0, but we're going to talk about a theorem that lets us extend this so that this is true for any simple closed curve, is 0. Which is not very exciting, right? I integrate these analytic functions and I get 0 out the other side. Well, maybe we should check the other case. Or the n equals 1, n equals minus 1 case. What happened in that case? If this was minus 1, and I started from here, so I get the integral around c of 1 over z dz, then that gets me the integral from minus pi to pi of 1 over r e to the it times I r e to the it dt. Everything cancels. That's gone, and that's gone, and that's gone, and that's gone. This I survives. And I've got I times the integral from minus pi to pi of dt, which is 2 pi I. So there's one single case where that integral turns out not to be 0. And this seemingly innocuous observation turns out to be the core of all of the rest of complex analysis. Seriously, this observation that this happens is the key to unlock all the rest of it. So we're going to keep that fact in mind. So as we go forward, we're going to keep coming back to this idea. Okay, questions about this stuff. This is the level at which this type of mathematics is done in complex analysis now. When you start doing computational integration, this is kind of what it looks like. You might have more concrete functions, but the idea of taking something like z to the n and plugging a parameterization into it and then calculating through, that's what it's going to look like when we get off the ground with our complex integrals. Yep.
When it has the circle, does that just mean it's on the closed?
Yeah, it's just it's a highfalutin way of saying this is an integral around a closed loop. Yeah, so that symbol is special because integration around closed loops is so important that we emphasize when we're doing it. Yep.
Do we need the closed curve to cover 0? Or the origin?
In this, no. Actually, not in this case. I mean, okay, in this case, yes. In this case, absolutely, because like it's going to turn out to be the case that the loop has to contain the asymptote for the function. So yeah, notice I didn't include this up here in this one, right?
Right.
So yes, in this case, it absolutely matters that that there's an asymptote of the function, the circle goes around it. Yep. If you guys have taken a topology class and never seen winding numbers before, or homotonic groups or fundamental groups, this is actually where the idea was born. So the study of homotopy theory and topology actually comes from complex analysis originally, which is weird. Okay, if you have no idea what I'm talking about, then you will someday, and it's cool. And then you can tell your angry topology instructor that your complex analysis instructor said the complex analyst did it first. Okay. So the goal of the previous part of the class, we pointed out that it's annoying to have to use parametric integrals, right? Parametric integrals are obnoxious. And we don't ever do those in real calculus, right? In real calculus, for the most part, sort of in a like naive real calculus, we use a theorem called the fundamental theorem of calculus, which says if f prime is equal to f, then the integral from a to b of little f is equal to f of b minus f of a, right? In real calculus, we don't parameterize things when we have antiderivatives. We just plug in. right? Now there's some conditions that you need to have here, right? You really want AB to be finite. You need F to be integrable. So, but the integral of F exists in many situations. F, Riemann integrable. So when we're faced with a situation like the one we did last time, where we integrated from over C of a function like, was it z plus I? Was that the thing we did last time? Is z plus 1 dz, where the contour C was the straight line that started at I and ended up at 1. It's actually not hard to find an object that when we take its complex derivative, z plus 1 falls out. Right? I mean, that function, z plus 1, has a complex antiderivative. It has a function that if we take its derivative, z plus 1 falls out. If we call f of z equal to z plus 1, and I just write down f of z is equal to 1/2 of z squared plus z, that certainly is an antiderivative of z plus 1 in the sense that the derivative of this is equal to that. F is an antiderivative of little f. F is a complex antiderivative of little f. Another word for complex antiderivative that you might see is a primitive. So Johnson uses that word occasionally, but what he means is antiderivative. Okay? And so maybe there's conditions on which we can say that the same rule applies, right? Like the goal here, or the golden dream, I guess, would be, boy, it sure would be nice if instead of having to do this, where we wrote down, oh man, z of t was equal to I plus t times I minus 1, and then you put that into that integral, so you get the integral from 0 to 1 of I plus t times I minus 1 plus 1 times dt, which is I minus 1 dt. And you grind that integral for a while, and what pops out the bottom is 2 minus I, after you do a bunch of algebra. This is what we did last time. We did this example last time. We plugged in z, we plugged in z prime, we integrated that function, and we ended up with this complex number that fell out the bottom after a whole lot of stuff that I didn't do because I was too lazy to do a bunch of complex arithmetic on the board. Right? But that's what happens. Sure would be nice. Sure would be nice if we could do that. So I mean, we could try and see. Maybe if we have a hope that the fundamental theorem of calculus might be true in complex analysis, we could just try it. Maybe, and then in the calculus 1 way, having shown it's true for one number and one function, it must be true for all functions and all numbers, right? That's the proof by n equals 1. Well, let's see. So in that case, it wouldn't really be the integral from 0 to 1. It would be the integral of the point that you started at to the point that you finished at. That's what we want to be true, right? When we do it over here, we mean the left endpoint to the right endpoint. So we would still want to say from the starting point to the endpoint, right? So maybe if we naively, let's just, this is the way math is discovered, is you just try things and see if you even believe they could be true. Let's evaluate this function's antiderivative. All of this stuff is lies I'm writing right down the board right now. So we're guessing. We're in the spirit of Cauchy. We're just trying things. And then I'm going to use this integral symbol, and I say, well, where did I start? I started at z is equal to I, and I ended at z is equal to 1.
You're missing a squared, right?
Yeah, there's a squared right here. Okay, so maybe if we're lucky, we'll believe, let's see, 1/2 of 1 plus 1 minus 1/2 of I squared plus I. That's 1/2 plus 1 minus 1/2 minus I. Is that right? I missed the negative sign. No, that's minus 1/2, so it's plus 1. Oh, 2 minus I. Interesting. Okay. Maybe it's true. Maybe I could actually do this. Now notice, nothing I wrote up here has been justified yet. I haven't told you this is legal in any way, but at least we've got some hope that instead of having to do this every single time that we do a complex integral, maybe we can find conditions on which we can actually do the calculus we already know. Notice, I did this without referring to the underlying parameterization at all. All I needed to know was the antiderivative existed, and the beginning point and the end point. And I could basically follow the logic of calculus 2 when I did this. So if this was to be true, which, I mean, I don't know why I'd be up here saying it if it's not ultimately going to be true, we would call this like the complex fundamental theorem of calculus, the fundamental theorem of complex functions. So this is our sort of our current dream, is a fundamental theorem of complex functions. Because if that was true, then we'd have both sets of tools available. Yep.
For this very specific case, because you just used the endpoints, does that imply you could have used any path on that specific?
That is a massive feature. So yes, it doesn't matter how I did it, right? And that's a huge piece of why this is all working, right? The fact that I just used the endpoint. Notice here, I picked a specific contour and plugged it in, and 2 minus I came out. But when I didn't refer to the path at all, I got the same answer. And that suggests that it didn't matter how I got from the beginning to the end. That I could have done anything I wanted, and as long as I started at 1 and ended at 1, I would have the same value. And so, if you have in your head any inkling of what are called path-independent line integrals from vector calculus or calculus 4, this is what is going on in the background. It's like, yep.
Is that why it was 0 when we did it on?
Yes, actually. In fact, it is y, because if we have path-independent line integrals and I integrate in a circle, then my beginning and end point are the same, and this would imply that I get 0 out for a sufficiently nice function. So yes, it's all kind of a piece, right, what's going on here. Okay, so the next thing we're going to do is we are going to try to show that this specific case that we lay out here is actually true in general, that I can do this often. As long as I know certain things about the domain of the function and where that curve sits inside of the domain, everything is okay. Sorry, this room is set up so badly for you guys over here on this side of the board. This is ridiculous. Should make everybody just like slide this way. I know, that's what I mean. It's like this. I mean, this classroom is a good illustration of entropy, right? Like, it doesn't matter what these desks end up looking like. They just scatter through the room like a gas expanding as the week goes on. Okay, so that means that we need to lay out the idea of what are called simply connected domains. So we're going to look at the domain of F. Just like in the real fundamental theorem of calculus, the domain of the function matters a lot. The real fundamental theorem of calculus holds on bounded intervals, right? Bounded compact intervals. They have to be closed. I mean, we do all sorts of abuse of this, but really, it has to be a closed interval from A to B. What's up?
Yeah, this is the question. I feel like so many things that it keeps sometimes just like a closed compact interval, but isn't a compact interval always?
It is, and yeah, it is. It is. I mean, I'm repeating myself because I'm trying to. I mean, really, what you want is the reason that it does it is because one, that's not true in every set that you plug functions into. That's a special property of R, right? And in C, that's not true anymore because there's not really an analog of intervals. So what I'm doing is I'm highlighting the features that AB has that we want to carry over into the complex numbers, right? So I want it to be bounded, and I don't want it to be. And I'm going to want the. Really, we're going to be working with open domains, but the same idea holds. What you should think of is intervals turn into rectangles, basically, in the complex numbers, and also they also turn into circles, and it's the same move. But yes, it's repetitive. It's a good question.
Just making sure.
Yeah.
I'm not making stuff up.
That's right. No, I just love making people remind themselves of the Heine-Borel theorem at every opportunity. Okay, so the domain of F matters. And so we're going to define something called a simply connected domain. All right, somebody give me a What does simply connected mean? I know there's a lot of people out here that have taken all the classes that leads into this. Can you give me a non-technical definition of what a simply connected domain is? Yep.
You can draw a line from one point in the set to any other point in the
Okay,
set.
so it's a
without
set.
crossing
As
the
over,
boundary.
it's a set, and you can draw.
A line from one point in the set to any other point in the set without crossing a boundary.
That's a convex domain.
Set not simply connected also.
Without crossing the boundary. By line, do you mean straight line or do you mean path?
Straight line.
No, that's a convex
Oh,
domain.
okay.
All right, somebody else take a stab at simply connected. That's good though. You have this sort of that's an even more special version of simply connected domain.
I guess it's any path. Isn't it?
That's a path connected domain, which is also not simply connected.
I thought simply connected.
No, see, there's all kinds of domains. I'm going to draw 3 different domains, okay? So, this guy. So this is simply connected and path connected, but not convex.
Okay.
Here's one. Oh, this is a funny one. There's this one. Take out one hole in the middle. I've got this. No. I'm drawing a bunch of different sets as domains down, and we're going to talk about like what potential problems could be with these. This is a disk with one hole punched out. This is an annulus. Yep.
Is a simply connected domain one in which if you take 2 subsets that are completely disjoint and then a third subset, you'll be in both of them?
Wow. I don't have to think about that. I was actually looking for something slightly simpler. That's like not that actually might be true, but let me.
I don't know.
No. Let me. I can't even. I have to think about the words that you said. Okay. If you were looking at these things, what is the yeah?
Is this that any closed loop you can draw in the domain would be contracted?
Okay. So that's a fancier version of it. Any closed loop that you can draw in the domain can be contracted to a point without leaving the domain.
There's no non-trivial.
Right. If you like topology, it's like there's no non-trivial homotopy in the set. One way of thinking about it is it has no holes. It's a set with no holes in it. So if I drew any loop inside this set, so say I draw a loop inside here, any loop, can I deform that loop to a single point without leaving the set? So this is what makes it better than just than path connected, right? It's a loop connection. This set is path connected because any point in the set can be connected to any other point in the set, but there's loops you can draw in here that you can't bring to a point without passing out of the set to do it. So this is not simply connected. This one is not because there's a hole in here. So the intuitive definition is no holes. This is not simply connected because you can draw a loop in here. I mean, yeah, there are some loops in here that can be contracted to a point, but there's other loops that can't be without leaving the set to do it. So by contracting here, I mean you take the loop and you shrink it to a point. You're not allowed to cut it and roll the ends up. You have to keep it a loop the whole way. So this is not simply connected because it has a hole in it. This is a stupid example, but so the problem here is that there are no simple closed curves in this set that run through both sets. Right, so that you would just discard this one because it's dumb. I'm just this mathematical term for this is dumb. Well, you wouldn't do it because it has non-trivial topological intersections, right? So you have to be really careful with simply connected. It's definitely path connected, but there's no way to get a loop. I would say I would call these 2 things components of this, and then I have to think about if the definitions of topology allow this.
I'm just thinking if you have to draw it in the domain. Oh wait, is the center point included?
It's included, yeah. This one right here, I think, is simply connected. Although, I mean, it's not path. This is where I want to stay away from the technical definitions of it. Let's just pretend this doesn't exist. And I didn't do that because I don't want to start talking about topology. And you are correct, by the way, that actually has 2 components, each of which is simply connected. But if I take it out, it's not path connected. And so path connected is weaker than simply connected. So we want things that look like this. And they can look really weird and still be simply connected, right? So, for example, if I take this set and I punch one hole out of it, That's not simply connected because there's loops I can make in here that I can't contract, right? But if I took that same set and I deleted some more points, that set is simply connected. Because I'm not allowed to make a loop that goes, this line is not contained in this set, right? So a loop can't pass through this. So loops can look like this in here, but they can't go through this line because that's not part of the set. So this is not simply connected, but this is simply connected.
So is there always a way to turn a non-simply connected set to a simply connected
There
set?
is in complex analysis, for sure, right? This idea of like deleting extra line segments to turn things into simply connected sets and then taking limits, yes, we're going to be doing a lot of that.
Okay, so it's guaranteed to work with any
Yeah.
geometry.
At least in the basic setups that we have here, we can always do this. We can always cut a domain with, at least when we have a domain where we've deleted points like this, we can always chop it up in such a way that the thing that results is simply connected, if we're careful. Yep.
There would probably exist like some really messed up domains where like no matter how small you chop up, it'll never be something.
Sure, I mean, there's pathological examples, but I want you to think of disks with holes punched out. So yes, you're right. The thing is, like, we're broaching on like these questions of topology that I really don't want to get into. But yes, in fact, you want to challenge, draw me one. Find me a set that you can't disconnect into a simply connected set.
That'd be pretty tough.
Wait,
Trevor, just lost the news.
Okay, so in the case that you have a simply connected domain, so for those of you that this is like sort of like an like abstruse conversation here, just think simply connected means no holes, right? I've put no restrictions on how the domain curls. I don't care if it touches itself like this. There's no restrictions on anything other than the fact the domain has no holes in it. So that's the intuitive way of thinking here is simply connected means no holes in the domain. And we're going to actually be using the idea of taking domains with holes and taking the domains apart to make them simply connected as we study contour integration. So it matters that we're starting with simply connected. Okay, so here's our big theorem for the day. Theorem. So in Johnston, he calls this the fundamental theorem of complex functions. So suppose a continuous function f is the derivative of an analytic function capital F on a simply connected domain. All right, so right away you're going to say, well, that's a pretty strong assumption. Like, we're going to say f is the derivative of an analytic function. But remember, complex analysis is the study of analytic functions. And so I don't need a theorem that works for general functions. I need a theorem that works for analytic functions, right? So this assumption is natural in the context of complex analysis. So suppose you've got a continuous function. It's the derivative of an analytic function on a simply connected domain. Then for any piecewise smooth curve C inside D beginning at Z equals A and ending at Z is equal to B, and then I'm going to use the excellent pedagogical technique of splitting the theorem across two columns because that's as one does. Then the integral over C of f dz is f of B minus f of A. And these are the assumptions that we need to have in place to assert that we can use the complex FTC. Okay? So you must come as the derivative of an analytic function. The domain has to be simply connected, and that matters because there's functions that we want to assume that have domains where, say, like f of z is equal to 1 over z. We have to be careful with something like this because f of z equals 1 over z. The natural domain would be to say, oh, like take a disk, but then delete the middle. This won't apply there. Okay. And for any piecewise smooth curve, okay, so the curve has to be piecewise and smooth, which means it's basically a picture that looks like this. This would be a situation in which it applies. We have a domain D, which is simply connected. We have a piecewise smooth curve inside of it. C, in this case, it's a loop, but it doesn't have to be. In that case, the fundamental theorem of calculus applies. Of course, that immediately causes problems. Because we just went through an argument where we were talking about 1 over z. We're talking about this function. And in fact, we integrated that function on a circle that contained its asymptote. So what did we just do when we did the parametric version of that function? So we just did this. We just did the integral over c of 1 over z dz, and we said that that was equal to 2 pi I on the parametrized curve for c, which was c is equal to r e to the it, where t went from minus pi to pi. That was easy to see why that happened, right? This was the parametric equation we just did, or the parametric integration we just did. We put that function in here, we calculated it directly, everything canceled, we got 2 pi I. What is the issue with trying to apply the fundamental theorem of calculus here? There's a hole in the domain.
Wait.
I mean, we did a curve. The basic picture of what we just did was this. That was c. But there's this problem where that function has an asymptote at z equals 0. Well, this function has to be analytic on a simply connected domain. It's not analytic on there. Shouldn't we be able to... I know what the antiderivative of 1 over z is. I hope. We did this on homework last time, I think. What's the derivative of... If I integrate 1 over z, what do I get? Log of z, so it has an antiderivative. The antiderivative is analytic a lot of places.
But not on that line.
Not on the line, including, it's certainly not at 0, and no number on the negative real axis either. Crap! I want to be able to integrate 1 over z and write log z and put 2 pi in and 0, or pi and minus pi in, and have the answer still come out to be 2 pi I. That doesn't make any sense to me that I can't do this. Yep.
Can you punch out a circle and draw the line?
Oh, this domain that I wrote right here. Yes, let's refer back to this for a second. So, yeah, you're right. This is how we're going to fix the problem. So, the problem that I'm pointing out here is I have this parametric setup where we showed that this was true. But the natural way to want to show this is true is to do it this way with the antiderivative. And they should both agree with each other if this is a notion of calculus that makes any sense at all. Right? The parametric setup for the integral should agree with the antiderivative fundamental theorem of calculus. And if the fundamental theorem of calculus can't handle 1 over z, then this is not very good calculus. Right? This is the problem. Okay. So, how on earth are we going to fix this? Well, I want you to think for a second about where the log of z is actually analytic. Is the log of z analytic on that set? So remember, when we wrote down f of z, which is equal to the log of z, which is equal to the natural log of the length of z plus I times the arg of z, what we pointed out was that arg z has this issue where when you come at it from one side, it's minus pi, and when you come at it from the other side, it's positive pi, right? So this is actually not a function that's even continuous on this line right here. Right? Certainly it's not defined at 0 because log of 0 doesn't mean anything. And it can't be defined over here because, or we don't consider it over here because if I approach from this side, the arg of z looks like pi. And if I come from this side, the arg of z looks like minus pi. So it's not continuous across that line, and if it's not continuous, it can't be analytic. So what we say is, this is analytic everywhere except z is less than 0. Really, zero and negative real numbers are out, right? I can't evaluate log on anything on this negative real axis right here. But as long as I don't do anything else, it certainly looks like it's analytic on this set as long as I don't include those numbers, right? I actually might have time to finish this. All right, so I really, really, really want to integrate 1 over z and get log z and calculate it. So let's look at a set where we're going to use this domain. We're going to assert that this is the domain that we're using. And the curve that I'm going to use is going to look like this. So here's the domain of the log z. So log z is analytic on this entire set, right? Everywhere except that line, log z is analytic. Is that okay? So it's not analytic on the negative real axis, but it's analytic everywhere else. Well, let's set up a curve that looks like this. Let's start at this point right here, and then let's integrate in a circle that goes around this way and stops right there. Does that make sense? Is that path that I just drew entirely in the region where the log of z is analytic? Oh, that means I could use the fundamental theorem of calculus to evaluate it. Because on that path right here, this path C, f is analytic over the set containing C. Is that set simply connected?
Yeah.
Sure, I can delete that line right there and have a simply connected set, right? Any loop I draw inside that set I can retract because I'm not allowed to go around this asymptote, right? So no loop I draw can contain that asymptote. Well, that means if this was the point B and this was the point A, it should be the case that the integral over this path C of 1 over z dz should be equal to the log of z where I plug in A and then I plug in B. That should be true. The fundamental theorem of calculus applies here. F is, and this function integrates to this. This is the antiderivative of that. If you take the derivative of log z, you get 1 over z. Which also begs the question, what the hell happens to the argument when you take the derivative? Which is something you should keep in the back of your mind. This should work. 1 over z is perfectly nice on this set. Log z is analytic here. This derivative is equal to that. So the setup for the fundamental theorem of calculus holds, which means this is equal to the log of b minus the log of a. So now, because I am probably out of time, so I'm going to have to leave this off slightly here. So the question is, what should happen? What should happen if I let b and a approach each other in the limit? This point we think of as being, this is like r e to the I pi plus epsilon. Or pi, it's a little bit less than pi, right? So this is like e to the r pi minus 1 over n. And if I wrote that point right there as r e to the I minus pi plus 1 over n, think about what happens as you rotate those points into each other and evaluate this difference of logs. I'll leave that for next time. Okay? And if we're lucky, and calculus works right, this will be equal to 2 pi I. And this method of working like this, where I have to work around these places where the function's not defined and work with these limits, this is an idea that's going to show up, again, regularly when we're working with integrating functions on places where they're bad. All right, if you're interested in reading ahead, this actual exact argument is in the textbook in this chapter. Okay?